Hello. In this section, we look at using permutations and combinations, mostly a focus on combinations, but you could see how it easily could be extended to permutations, in order to count probabilities, calculate probabilities. So in order to understand really what we are going to be doing, you have to just go back to the definition of a probability of success. So the probability of success is really the number of ways to succeed divided by the total number of possible outcomes. That's what a probability is. Ways to succeed by total number of possible outcomes that could have even occurred. Using that definition, you really have all you need accompanied with the prior topic in order to calculate some probabilities. Be aware we're going to introduce a little shorthand notation. So another way of saying 5, choose 3, or a combination of selecting 3 items from 5 total, we can write it as the following. So we use parentheses and we put 5 over 3. It's just a shorthand notation for writing combinations. But note, this is only for combinations, not permutations. Okay, so here we go. Situation number 1. Let's say the student council consists of 20 members. There will be a student body president and a vice president selected. Each member is equally likely to serve in either of the positions. What is the probability of randomly selecting 2 members who currently hold the position? If they currently hold it, what's the likelihood that they're going to get, reelected in those positions, or one of those positions? So does order matter here? Yeah, order matters here. So we're going to be counting with permutations. The order matters because, one's a president, one's a vice president. So probability of success, number of ways to succeed divided by the total number of possible outcomes. The very first thing we're going to do is organize the information into the 2 groups that we are counting from. There are 2 current people in the role, and there are 18, because I think it was 20 people total. Yep, 18 people not currently in the role of president or vice president. So organize our information. We're going to do this almost for all of the problems. Second thing is we're going to count how many ways to select the desired divided by, just going to kind of talk our way through it a little bit step by step. Count how many ways to select the desired amounts divided by the total number of possible selections. So probability of success to start, which means from the 2 people that currently have the role, I need to select 2 of them. And so we would do 2 permute 2. And remember in math means multiplication in probability. So and from the 18 people of president and vice president, I need to select 0 of them. And I need to divide it by selecting 2 people from 20 out of the total. Calculate each of those. 2 permute 2, this piece right here is 2. 18 permute 0 is just 1. There's only one way I can select the 18 people, or 0 from the 18 is I just don't select them. Divided by 20 permute 2, 20 permute 2, divided by 2, or 2 divided by that is going to be 0.0053. So I end up with highly unlikely, that's about 0.5% likelihood that if the 2 current members currently hold it, what's the likelihood they get reelected? If all people are equally likely to get elected, very unlikely. So that's the first example. So I think the rest of them are combinations. I wanted to lead off with an example of a permutation. Permutation here since order mattered. Second situation, let's say, so a flush in poker is when all 5 of your cards are the same suit. What is the probability you are randomly dealt 5 hearts from a deck of 52? So in order to find the probability of getting 5 hearts, I need to divide by the number of ways to get 5 hearts divided by the total number of possible 5 card hands. So does order matter here? No, the order of the 5 hearts does not matter. So we're going to be using combinations. It doesn't matter if you got 4, 5, 9, 10 ace, or if you got 5, 4, 10 ace 9. The order of which you got them doesn't matter. Just the fact that you got 5 hearts matters. So the first thing we're going to do is organize the information in the 2 groups that we are counting. We're only counting hearts and not hearts. And in a deck, there are 13 hearts, and there's 52 cards possible, so that means there are 39 not hearts. In order for me to be dealt a flush in hearts, I need to count the number of ways to select the desired amount divided by the total possible outcomes. So I want to take the number of ways to choose 5 hearts and 0 non-hearts divided by the number of ways to get 5 cards out of 52. So the first part is going to look like this. From the 13, kind of color code this, from the 13 hearts, I need to choose 5 of them. So 13, choose 5, and means multiply. From the 39 not hearts, I need to choose 0 of them. And down below, from the 52 cards, I need to be, choose 5 to be dealt. So calculating, 13 choose 5 is 1,287 times 1. Down below, 52 choose 5 is 2.5 million, essentially. Calculate it, and you end up with the following probability. Highly unlikely. That's why flushes are worth so much. You could also write this in the following way. So what we did right here could be written as 13 over 5. It's not a fraction. You do not write a division symbol. You do not do that. It's 13 over 5, and we put parentheses around it. And that means 13 choose 5, and from the 39 hearts, we need to choose 0, divided by, from the 52 cards, we need to choose 5 to be dealt. So this is a shorthand notation of writing what we did up above. Really, it's saying we don't need to write the C's because we know they're combinations. It saves us from writing the C's. Going to give you a chance to try. So almost the exact same scenario. I want to know what's the likelihood, the probability you were randomly dealt 5 hearts, but not from a deck of 54, but a deck of 52. Let's say the jokers are still in there. They haven't been removed. So see if you can just manipulate our prior example slightly in order to calculate what the new probability would be. Maybe think to yourself beforehand, should this probability be higher or lower? So pause the video, come back and see how you did. So here we go. We need to know the number of ways to get 5 hearts. So from the 13 hearts, we need to choose 5 of them. And from the, now it's going to be 41 not hearts, I need to choose 0. Well, that's still 1. Divided by 54, choose 5. So this is going to be a bigger number. My total should be slightly smaller. It's kind of hard to see because my result was so small anyway. We end up with 0.0004. So 13 choose 5 divided by 54 choose 5. You'll see this number right here was my 52 original plus my 2 new, jokers that were in there. Just try a couple of other examples. Just kind of the more examples you see, the more likelihood you'll kind of understand what's going on. So let's say this. In a typical batch of 100 bananas, the company knows 15 will be bad and 85 will be good. If a grocery store is going to put 20 out for sale, what's the probability that 5 will be bad? So here's the overall batch. I know there are 85 good ones and 15 bad ones. What's the likelihood? Select 20, and from those 20, 5 of them will be bad, which means 10 will be good. If I'm doing 20, if I'm putting 20, 5 will be bad and 15 will be good. So what's the probability? I'm going to pick 20 of them to put out there, which means 15 are good and 5 are bad. So up top, I need the number of ways to choose 15 good from the 85 goods in the entire batch and 5 bad from the 15 bads that are in the entire batch, divided by the total number of ways I could have chosen 20 from the 100. So first part, number of ways to choose 15 goods from the 85. So that's 85, choose 15. And I need to multiply. From the 15 bad in there, I need to choose 5. Divided by, put equals, there were 100 total, and I'm going to choose. See, there's a pattern that goes on. So 85 and 15 up to the 100. 85 goods and 15 bads is the 100 total bananas. Down below, the numbers need to add up to the bottom as well. 15 goods are selected, 5 bads are selected, and 20 are going out, for sale anyway. So now I grab a calculator. I need to calculate. So I'll do the first one on screen, and the rest I'll do off screen just to be a little bit more efficient. But the first one's 85. Choose, what did we see? 85, choose 15. Number's large. Actually, what I'm going to do is I'm going to kind of on screen. So grab what we just did. So 85 math, choose 15. Times that by, the top part was 15, choose 5. So I'm going to put parentheses. So 15 math, choose 5. Whoa, no. Three, yep. Choose 5. Find what that is, even larger. Divided by the total. So from 100, I am choosing 20. And the likelihood I put out that arrangement is about 10%, 0.1. So about 10% likelihood that that actually occurs, of putting out 15 goods and 5 bads in it out of the 20 from the 100. Second scenario occurs when whenever the Powerball is drawn on a biweekly basis. So the largest lottery jackpot in U.S. history was in January of 2016 was for 1.6 billion. When won, the first five numbers are chosen from 1 to 69, and the last number, Powerball, is chosen from 1 to 26. What is the probability of purchasing the winning ticket with one purchase? So what we need to do is calculate, well, there's only going to be one winning ticket. That might be easy enough to recognize. We really need to calculate the total number of possible tickets that can occur. So for the first five, it's going to look like this. In order for me to get a winning ticket, it means from the first five numbers that were winners, so for the first batch, there's numbers 1 to 69. Five of them are winners, 64 are losers, and then they do the Powerball number. You have to match that as well. There's one winner and 25 losers because there's 26 numbers in total. So for the first five, from the five winners, I need to choose five of them. From the 64 losers, I need to choose 0 of them. Well, choose five is 1. There's only one way I can select five winners from the five, and 64 choose 0 is also 1. Over here, for the Powerball, from the one winner, I need to select it. That's only going to occur in one way. Choose 1 is 1. From the 25 losers, I need to choose 0 of them. And again, that's 1. This top part just shows there's only going to be one winning ticket. Down below are the total number of possible tickets. So they're from the 69 total numbers, I need to choose 5 of them for the first part. And then from the 26 Powerball numbers, I need to choose 1 of them down below. So these, I need to calculate these two numbers right here, and they're going to multiply each other. When I do that, I end up with, up top I get 1, down below I get, 11.2 million for just the first five numbers times 26 numbers for the Powerball, and when I calculate that out, 0.000000003. So highly unlikely. That's why winning the Powerball is such a big deal. That's why the jackpot can get so large. It's highly unlikely that a individual would win. And I believe this is our last one, and then I'll have you try one. So last one. A shipment of 20 keyboards contains 3 defective units. This is very similar to the kind of banana situation. You got good and bad bananas, and a lot of these are very similar. When you're counting things, you're usually counting good and bad items. In our last example, they were good and bad items. It was winning numbers and not winning numbers. So a shipment of 20 keyboards has 3 defective units. A company purchases 4 of the units. What is the probability of buying at least 3 non-defective items? Probability of buying at least 3 non-defective items. At least 3 from 4 means what's the probability they got? 3 non-defectives or 4 non-defectives. So we need to calculate each of them and then add them together. So the likelihood of getting 3 non-defective items would mean from the 17 not defective ones, they need to get 3. From the 3 defective ones, they need to get 1. There's an and between, and divided by from the 20 in the total, we were selecting 4. We bought 4 of them. Or means addition. I could have had 4 non-defectives, which means from the 17 goods, I need to get 4 of them. From the 3 bads, defective being bad, so this is kind of good. Not defective is good. Defective would be bad. From the 17 goods, I need to get 4 of them. From the 3 bads, I need to get 0. From the total possible, there was 20 of them in there, and then I bought 4 of them. Then I just calculate all of these individually, multiply the top parts, divide it by the bottom, find the left, the probability of getting 3 goods, find the probability of getting 4 goods, and add them together because it's one or the other. So 680 times 3 divided by 4845 plus 2,380 times 1 divided by 4845. Calculate the left one, calculate the right one, add them together. And when I do that, I'm going to end up with 0.9123, or 91% chance that I get 3 goods or 4 goods, which is at least 3 non-defectives, at least 3 good. Last one, I'm going to give you a chance to try. 2 light bulbs are selected from a random lot of 80, of which 6 are defective. So 6 are bad. What is the probability that 1 is defective and 1 is not defective when you select 2 of them? Give you a chance to try and then come back and see how you did. So let's fill in the table first. We said 6 were defective, which means 74 are not defective. 74 are good, 6 are bad, and you're going to choose 2 out of them. What's the likelihood you get 1 good and 1 bad? Well, this is what it looked like. First off, order doesn't matter. Whether you got a good or a bad or a bad or a good would be the same. From the 74 goods, I need to get 1 of them. And from the 6 bads, I need to get 1 of them. Divided by from the 80 in the lot, I was selecting 2. Then I just run the calculation. There's about a 14% chance that I'm going to get 1 good and 1 bad when I select 2 from that lot. And that is it for today. Thank you very much, and have a good day.